My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's session on a comparative study of graphene in composites, something that is really interesting and very timely. We are joined by representatives of Vibrance, that would be Paul Redinger, and Jason Gibson from Composites One. These two companies were critical partners in this project, and you'll learn much more about their roles, the individuals involved, and the outcomes from today's session. For those of you who are not familiar with the Graphene Council, we are a global trade and professional body representing the graphene sector, founded back in 2013. So we've been at this for almost 10 years now. We are involved in every aspect of graphene development and commercialization, including the setting of standards through the ISO, ANSI bodies primarily. We track the entire graphene sector. We have a community of over 30,000 material scientists that work with graphene material. And so if you have any questions about graphene materials, sourcing, supply, standards, testing, verification of graphene companies, we're the resource to turn to. Graphene is an exciting material because it can be applied to so many different applications. And here you see not an exhaustive list, but a pretty comprehensive list of all the different types of applications where graphene has utility and can make a real difference. And composites is one of those, and composites is also one of the most important and most significant of those vertical markets, and that's what we're focused on today. There is different type of graphene material for different applications, and this gives you a rough outline of where those different types of bulk graphene or multi-layer graphene can be applied. That's in the blue segment. You have monolayer or single layer graphene, which is primarily for electronics, sensors, and that type of application. And then you have a combination that could be single or multi-layer. The fastest growing and most important sectors that we see for graphene are composites and plastics, incorporating both thermoplastics and thermoset materials, energy storage, which is both batteries and supercapacitors, elastomers. Typically, you think of tires, but also includes seals and gaskets, coatings, especially for anti-corrosion properties. Graphene has excellent thermal management properties, and we see really strong growth in the sensor sector, which is a different type of material than from what we'll be discussing today. It is graphene, but it's mostly that monolayer, single layer material. But that's a really important segment, is the sensors. Graphene can be used in many components within the automotive sector, and thank you to the University of Manchester for allowing us to use this graphic. You see graphene in all parts of the automobile, and for those of you in the composite sector, you can appreciate how important this is, because composites obviously are posed to comprise an ever-increasing part or components of the automotive sector, especially with the transition to electric vehicles. The same can be said for the aerospace sector, where lightweighting and strength is incredibly important. And that's one of the extreme advantages of using graphene to enhance another material, is it adds and imparts strength at extremely low load factors, allowing you to reduce the weight of the part. So again, for aerospace, weight is everything. And this is why it's so exciting also for that type of application. There are, of course, many others like wind turbines and many other applications where strengthening the composite material gives a real market and competitive advantage. Now, when we refer to graphene, I just want to make sure that everybody understands that there are different types and forms of graphene, and we're talking about CVD or monolayer graphene is literally a single atomic layer of sp2 bonded carbon in a crystalline structure. And then there are different types of graphene that are recognized under the ISO standard, which includes up to and including 10 layers of carbon. And so you have everything in between in terms of the number of layers. And then you can also differentiate graphene materials by the lateral size, the width and length of those flakes, if you will, or those crystals. Can differentiate from sub 1 micron to multiple microns in lateral dimension. You also have additional types and forms of graphene, including a graphene oxide material, which is produced with specific methodology, and it has approximately 35% oxygen by weight. This is an important material because it takes graphene, what is typically hydrophobic, and makes it hydrophilic because of the oxygen. It also takes graphene, which is highly electrically conductive, and makes it an insulative material. It's no longer conductive, again, because of the oxygen. You then have reduced graphene oxide, which is what it sounds like, a graphene oxide in which the oxygen has been reduced or removed. Graphene can be obtained, used, and sold as a powder, a solution, or a paste. So it can be dissolved into a solvent, it could be water or some other solvent, or it could be in a paste form. You have graphene nanoplatelets, which exceed the 10-layer count and are still usable from a commercial point of view. And then we have functionalized graphene, in which some chemical additives or elements have been added to the surface or the edges of the graphene material to enhance its behavior. And this is extremely important when you're talking about dispersion or incorporating graphene into a matrix, especially if it's maybe a fiber reinforced composite and you're using functionalization for dispersion or adherence to the fiber reinforcement. So the Graphene Council is independent, and we have conducted in this project an independent head-to-head testing of 17 forms of graphene into this system. It was a blind test. In other words, the test participants and our partners were not aware of the individual materials that they were given. And when they were sent to the University of Maine did not know whose material was being tested. They were given the master batches to create test coupons and then produce the results. And the objective of this test was simple. We wanted to know, in a methodical scientific method, does graphene impart a significant improvement at very low load factors in a composite material? And that's what we've done, and that's what you're going to hear about today. And with that, I'm going to turn over to Paul, who's going to talk about Vibrance's, what was previously ChromaFlow, Vibrance's participation in this test, what they did, and the implications of that. So Paul, if you want to go ahead, and I'll do the slides for you, just let me know what you'd like to go on.
Thank you, Terrence. Yeah, as Terrence indicated, I'm Paul Redinger. I'm the technology director for the legacy ChromaFlow. If you just back up just 1 second, Terrence. I just want to emphasize, I come from the ChromaFlow side of this, and I want to mention that ChromaFlow and Faro and Prince earlier this year, 3 different companies combined to form Vibrance Technologies. And we're pretty excited about some of the synergisms that we're starting to get out of this. And there's a lot of things that we can do that I think are pretty important for the industry and composites, and also the nanotechnology as well. Okay, so Vibrance has a purpose, which is to bring in color. I come from the color business unit of the organization, and we want to bring performance. I'm certainly trying to do that. And we also we call catchword vibrancy to life. Our vision is to be an enduring, sustainable, world-class specialty chemical and materials company. And our values are safety, first and foremost, commitment to customers, our people, sustainability in the environment, which we believe this plays a significant role in, and commitment to excellence. And of course, you can't have any of that unless you have integrity and ethics and trust. Our business segments involve the advanced materials, which works in engineered minerals for metallurgical and brick and glass and manganese for specialty chemicals. We also work with color solutions. That's probably the largest segment. That's the part that I come from. This is the part that involves ChromaFlow and part of Faro. We produce color dispersions, and in the current context, we produce dispersions of very small, very fine particles. We also produce additive technologies and additive blends and specialty chemical mixtures for very particular applications, especially as related to the coatings and composites industries. And then we also have a performance coatings that's really basically evolves around glass coatings. It's for industrial and porcelain enamel, things like maybe your stove or your refrigerator or something like that, or an appliance might be coated with a coating that we produce in Vibrance. So what does this have to do with graphene? Graphene, as it happens, is an area of intense research within the ChromaFlow legacy business unit of Vibrance for the past decade. I want to emphasize, we don't make graphene, but we do disperse very fine particles, right? And we've been dispersing carbonaceous nanoparticles for the past quarter century. So we do logically move into the field area of dispersing, things like graphene, and we do disperse it. So, and another thing we do is we continue to experiment with customizing graphene and customizing graphene dispersions for very specific applications, including transportation, electrical, battery, coatings, and other applications as well. So as it relates to this project, we received 19 encoded graphene samples. We processed them, and we didn't know exactly what they were. We just saw that they were samples, the little 50-gram sample. And we processed these samples into stable, rheologically consistent, processable liquid master batches in bisphenol F resin for the purpose of this study. We took significant steps in this process to make sure that we were deflocculating and deagglomerating, but not otherwise damaging the particles that we were doing, and we processed them all on the exact same piece of equipment under the exact same parameters. Very specific loadings that we achieved varied somewhat according to the surface area of the graphene that we were working. But basically everything was handled as close as possible to exactly the same way without introducing additives or other variables into the process that might confuse or produce noise in our results. So once that was done, we then shipped the samples to the University of Maine for further testing. At the University of Maine, I'll give you an overview of what was done, and then Jason will be speaking specifically to the results. But at the University of Maine, the samples were let down from our master batches to concentrations of 0.5 and 0.1% in BizF epoxy resin. And then after they were let down into the resin, they were mixed using a high-speed orbital mixer, and they were degassed under vacuum. Once that step was accomplished, there was a curative package that was introduced. We used a common amine ratio stoichiometry of amine to resin for all samples. We did not account for a variation in the functionality of the graphene itself because this was a blind study. The samples were then mixed, poured onto molds at 60 degrees Celsius, cured for 1 hour, and then afterwards they were subjected to a 3-hour post-cure at 160. After that was done, they were then cut from molded panels and subjected to flexural and notched izod testing. So in general, I will say this, we saw a lot of variation in performance, but there were some specific gains that Jason will get into, as much as 35% gain in flex strength, up to 75% gain in flex modulus. And there were a few samples that, in spite of the significant gains to modulus and stiffness of material, exhibited little or no damage to notched izod value or toughness. So I will turn it over to Jason at this point and let him present the actual data and the results. Jason?
Thanks, Paul. So my name is Jason Gibson. I'm the Chief Applications Engineer at Composites One. I've worked in the industry for over 20 years, with 16 of those being with Composites One. Now I have the task, as he mentioned, of presenting the final results of our testing. But before that, I'd like to just take a moment to introduce Composites One to you. So Composites One is the largest composite-focused material management company in North America. On any given day, we're supporting our customers' needs by handling over 40,000 unique products from over 600 suppliers. But the key to remember about Composites One is that because we're not limited in our product offerings, we can explore the unique breadth and depth of composite materials we handle to bring you a comprehensive, integrated solution for your specific needs. Now, we do this by not only delivering the products quickly, but also supporting our team through hands-on technical support across North America. Now, this slide gives a good overview of the geography of our network, and you'll notice that we cover North America through stocking locally with 44 locations. Now, this means that wherever you're located, we could support you by not only stocking the material you need, but by helping you with technical support in your shop with one of our many local technical sales representatives. So let's go ahead and dig into the results here. So as Paul mentioned earlier, we had 17 sample materials shipped to the University of Maine for testing. These samples were anonymized, and no one, including myself, knew whose material we were testing, giving an unbiased, objective testing protocol. We took the 17 master batch samples that Vibrance did and blended them down to the 0.1% and 0.5% loading of graphene by weight into the BizF epoxy. We poured the samples into a mold and cured at 140 degrees Fahrenheit for 30 minutes, and then followed it by a 3-hour post-cure at 320 degrees Fahrenheit. The samples were then cut from the molded panels and tested for both flexural properties and impact toughness. In some of the samples, we saw great improvements in both flexural modulus and strength. Now, typically, when you improve the modulus of resins, you have a negative impact on toughness of the system due to embrittlement. And this was true for some of the samples. However, there were some that showed negligible impact to the toughness of the resin while providing excellent flexural modulus and strength improvements. So let's go ahead and dive into the details of the results. So let me just take a moment and explain the data we're looking at on this slide. So first off, along the left side, you'll see the sample numbers starting with a control sample that doesn't have any graphene enhancement. This will be the baseline that we compare everything to. The first few columns show the results for flexural modulus for both loadings of 0.1% and 0.5%. Then the next few columns show the flexural strength results, and then those final few columns on the right detail the recorded strains. Now, throughout, we've highlighted the results with colors for quick interpretation. So if you look at the 0.1% loading for flexural modulus, you'll notice significant improvements highlighted in green for samples 9 and 15 through 18, with results as high as 72%. Now, if you look at those same samples for flexural strength, you'll see that all 5 of those samples also improved the strength as well. If you look in detail at the 0.5% loading, you'll also notice many more samples that improved flexural modulus. However, the improvements were not as high as the 0.1% loading. Now, with that in mind, it's good to introduce the concept of statistical significance on the next slide. So I'm showing 4 different graphs on this slide. All 4 are for the 0.1% loading. These are the flexural modulus, the stress and strain, and the bottom right graph are the impact results. You'll notice each graph has a bunch of colored circles on the right. These tell us which results are statistically significant, which simply means that the differences in the samples tested and the control are significant enough that we can be confident that there's a difference. So if the circle is shown in red, it simply means that those results are not statistically different from our baseline, and so we consider the difference negligible. But if the circle is in gray, it means that the samples tested had enough of a difference from the baseline that we could be confident that there is a significant change in results, either positive or negative. So if we look at the flexural modulus results in the top left graph, you'll quickly notice the 5 samples I mentioned earlier have a significant improvement over the baseline. And their circles are in gray, reinforcing that they are statistically significant. And that's great news. Now let's take a look at the impact results in that bottom right corner for those same 5 samples and see if they affect the toughness of the resin. You'll see that samples 15, 16, and 17 all are in gray, meaning that they significantly reduce the toughness of the base resin, and that's not good. That's not what we want. But both samples 9 and 18 are shown in red, meaning that their impact on the toughness is statistically negligible. That's great news. It means that out of the 17 samples we tested, we have 2 that significantly improve the flexural modulus and strength with negligible impact on the toughness of the system. All right, so let's take a look at the same type of data for the 0.5% loading. So here are the same 4 graphs for our 0.5% loaded samples. Immediately in the top left graph of flexural modulus, you'll notice none of the samples tested showed any statistically meaningful change from the baseline, and all are in red. You'll notice that the spread of results is larger than the 0.1% loading we showed on the last slide. There is simply too much variation in results to have any confidence in them being different from the baseline. Now let's also look at the toughness results in that bottom right graph. Here you'll see that all of the samples showed significant change in the toughness, but it's in the wrong direction. All of them lower the toughness of the base resin. So in result, none of these results for the 0.5% loading show any great promise for us. So if we look at just the toughness results for both loading levels, you can see again that the 0.5% loading shows a lot of red and orange in the percent change. None of that is good. But in the 0.1% loading, you'll see a number of green results that are good, with sample 9 being one of them, and sample 18 being yellow at an 8% change. But that 8% change is not statistically significant for us to know that it definitely has an impact. 5 samples at 0.1% loading that showed significant improvement in flexural modulus and strength. Out of those 5 samples, 2 had negligible impact on the toughness of the resin. Now, I want to reinforce that this was a blind study, so there was no bias given to any graphene supplier. However, that also means that we could not optimize for any type of functionalization the suppliers may have done. And as we mentioned, in general, the 0.1% loading provided better results. Now, moving forward, our plan is to offer additional testing of other graphene samples. This will be done at the cost of the supplier and be done at the 0.1% loading for comparison to the original data. This will be done through the Graphene Council. We also have plans to publish in future peer-reviewed periodicals, so keep your eyes out open for those. And we want to look at other loading percentages to determine what is optimal. We know that 0.1% loading is better than 0.5% loading, but is the 0.1% the optimal load? And finally, we'd like to conduct testing in finished laminates. We predict improvements in any resin-driven physical properties like interlaminar shear testing, but we need to confirm in testing of the fiber-reinforced laminates. So we've presented a lot of information today, and I'd like to just simplify why this is important. We now know that we can offer a graphene-enhanced resin that produces a stronger, better material. And with that increased strength and modulus, you now have a system that may allow you to produce lighter parts and give the possibility of reducing your ply stack for a given design. Now, we do get a lot of questions about cost, and I can confidently say that due to the extremely low loading of 0.1% or 0.001, the cost of the graphene in the finished system is very affordable and is significantly less per pound than the standard bis-A epoxies at current market prices. Now, another selling point is that these are drop-in solutions. There's not going to be any change to your current process. You simply blend in the enhanced master batch into your base epoxy systems with standard mixers. It's simple and easy. Now, before we open up for questions, just a quick reminder of why you want to work with us. At the Graphene Council, you'll have an independent and neutral source of expertise on the supply chain. They're an incredible wealth of knowledge whose only goal is to promote graphene. At Vibrance, you have a deep, experienced team of experts with a deep skill set in tuning and compounding nanomaterials. And then finally, at Composites One, you can rely on us to partner with you every step of the way with a market-ready solution that we can stock locally for you while offering technical support in your shop as you implement it in your process. So with that, I'd like to open up for questions. We'll go ahead and look at the chat that you guys have been posting at, and I'll let Terrence kind of fill us in on what questions we might have.
Thank you, Jason. Nice job.
Thanks, Jason. Thanks, Paul. Really appreciate that. Well, let's get into the Q&A. If we have to go back to the slides, I can't bring them up, but let's see what we can address. So one of the questions, can we use in plastic recycling process and how? That's one of the first questions. It's not really directly related to what we're showing today, but I will answer that question because we do have case studies where graphene has been added to plastics in the recycling process and taking advantage of these improved strength characteristics that graphene brings. The short answer to that is yes, graphene has a role to play in plastics recycling. How to compound in polymers, and what do you do about color? And that wasn't one of the aspects that we really looked at, but Paul, I don't know if you want to address that on the impact that this might have on color.
I will comment
parts.
a little bit. Graphene, specifically on color. Graphene is something that is dark in color. The exact grade that you use can have an effect on the impact that it has on color. But I will say this, the loadings that we're talking about are low enough that you can, in theory, put color into this, and maybe you won't achieve a bright, brilliant, Corvette red, but you can maybe do some grays and maybe some browns and some other types of colors that might be suitable for your application. It's something we'd have to look at, honestly.
Thank you, Paul. And we are going to be looking at even lower load factors, so that there would be less of the material in there. Another question was, about how the materials were mixed, how dispersion was quantified, and was there any evidence of sedimentation? And I think, Paul, you have a lot of good experience on that. Some of this, I will say to the audience, we won't be able to answer every single question because part of this is tradecraft in terms of dispersion methodology. That's some of the intellectual property of Vibrance on how to do some of the compounding. That's where their expertise is. But we can't talk about this issue of whether we saw sedimentation because we did have samples that were kept for a period of time.
Yeah, and the samples that we actually sent off to the University of Maine did not have sedimentation. They were all uniform and homogeneous.
And can you talk a little bit, Paul, because I know you guys did this, is how you examine the material to determine that there wasn't sedimentation?
Yeah, it was actually pretty simple. There's a dilution test that we can do that verifies whether a material is stable or not. And we performed we performed dilution test, and then the material passed the dilution test. We knew it was good material. It's a little bit of a proprietary test, but I've spoken about it in other webinars. And all the samples that we sent did, were clearly in suspension and not settled.
And I'll just add on the end at the University of Maine when we were there, those were still very well dispersed, and they had been, sitting there for a while. It wasn't just an immediately, transferred and used. It was sitting there for a while and still clearly dispersed throughout the system.
The rheology of what we prepared did not really allow much for settling. They were all prepared to a fairly consistent pseudoplastic rheological factor. And as such, they remained in suspension that way for an extended period of time.
So I think that aspect's important to understand, because the material could be prepared then as a master batch that would be shelf stable for a period of time, right? I think that's the important outtake.
We've done shelf stability testings for as long as 18 months on some of the dispersions we prepared and not seen any issues.
Yeah, that's important to know. There is a question about the percentage in the master batch, what you were able to achieve. And I think, Paul, maybe you could just speak a little bit to the range of values that you saw, because that was quite interesting. That's one of the interesting outtakes from this experiment.
Yes. Yeah. What people call graphene, is they think of it's all graphene, right? But it's really, there's a lot of different materials out there with a lot of different characteristics, from either platelet diameter, platelet thickness, also different levels of functionalization or oxidation or other things going on with their materials. And to us, it was all kind of a blind study, but the surface characteristics varied significantly. I would say, one of the things we did when we were preparing dispersions, we were looking at the surface characteristics of the material to see what we were dealing with, to try to figure out how to prepare the dispersions. And the surface variation ranged from probably 60 to 80 square meters to as high as probably 1,500 square meters per gram amongst the samples. So that's huge. I mean, an automotive carbon black will have a surface area of maybe 5 to 600 square meters per gram, and your tire will be maybe 20 or 30. So this is an even wider range than the range of carbonation, carbon blacks that are out there and available in the market, just in 17 little samples that we received. And so the actual concentrations that we produce varied from as low as 1% to as high as maybe 25% but they all had the pseudoplastic rheological factors that allowed them to remain in suspension.
Thank you, Paul. I have a question for you, Jason. One of the audience is asking what kind of epoxy resin was used. Did we try different resins? Can you just talk to about the resin that was selected and why that particular resin was chosen?
Yeah, so we went with the bisphenol F epoxy. We did that because bis F will give us the best physical properties, so we can let it down into a bis A and still do good results. If we started with the bis A, if we had an application that needed higher properties than a bis F, we wouldn't necessarily see those same results. So we decided to go with the bis F epoxy. We chose the Huntsman GY282 because of its use, and we regularly use that material. So that's why we chose that particular GY282 and why we went with the bis F system.
So I guess one of the questions would be, how translatable are the results to other systems? I mean, from our observations at Graphene Council, because we see a lot of performance data from individual companies that are shared publicly and also with us directly. And if you look at the polymer pyramid, we've had graphene go into PA6 nylon and it goes into PEEK. So there basically hasn't been a material that graphene hasn't been able to be integrated into. But Jason, do you want to speak a little bit more about your expectations on, different resin systems and that sort of thing, and the applicability of using graphene?
Yeah, and the fact that we saw, over 70% improvement in flex modules in a bis F tells us that we should see even better percentage results than a lower quality like a bis A type system. Now that's just for epoxies. For different resins, whether it's thermoplastics or whether it's a polyester, styrene-based resin, we'd have to do a different type of optimization. But for epoxies, I would suspect that we'll see even better, higher percentages for different epoxy systems as you go down in grade, basically.
Can I make one comment?
Of course.
The graphene is not like a single thing, right? There are a lot of different varieties of graphene that are out there. They have radically different properties. In a graphene that doesn't perform particularly well in one particular polymer matrix and one particular test under one particular set of conditions, might under a slightly different set of test conditions or slightly different polymer or slightly different system may perform extremely well. So I want to emphasize that just because a particular graphene in this particular study did not necessarily yield statistically significant improvements does not mean it's not a good material and that it can't produce good results, and it may be a slightly different application or area. And another thing too, it's, you know, if people were doing functionalization to the graphenes, we weren't accounting for that. And stoichiometry and cross-link density is another thing that can affect these types of results and have impact as well. So I mean, there's a whole it's a complex area when we start talking about, you know, optimizing graphene for one thing. But I will say this: we've seen enough data from this study and other studies that we've done that there's clearly an element of tunability to the material that allows you to reach across different applications and different polymer matrices.
That's a good point, Paul. And I just want to add on here. It kind of highlights the differences of what we're talking about here. So at Composites One, we want to have a off-the-shelf ready BISF enhanced slurry that we could sell to anybody they can use and see enhancement. But as you mentioned, if you started taking into account the functionalization, started optimizing for the particular system that the customer is using, you can get even better results. So that's where, you know, we can work with Vibrance and really optimize the solution, dial it into a specific system, or you could, you know, buy the system that we're going to have on the shelf and immediately see results by just dispersing in your BIS-A or other systems out there.
This is probably a really good point to emphasize to everyone that, you know, this study was not an end point. This was a starting point. This was to say, can graphene improve these kind of systems? Yes or no? And we did it blinded, non-optimized. So it was the least optimized way of doing it, and we still got good results. So I think that's important to put into perspective. There is a question from the audience asking what type of graphene it was which showed the better results. We have worked with our graphene companies to supply different types of materials. And I will say this, we're not going to identify whose material was what. That's not part of the study. We as the Graphene Council do know, of course, who submitted what samples, and then we blinded them before we put them into the project. We did receive materials that included graphene oxides, reduced graphene oxides, graphene nanoplatelets, functionalized material, 19 in total, of which 17 were tested, 2 had been withdrawn. So we have a really broad range of materials. And as Paul just said, some material that did not do particularly well in this exact scenario does not mean the material does not have promise for another scenario. There are some other questions that have come up, and I'll characterize some of them. People are basically asking why use graphene when other materials, a carbon black or some other additive materials, could be used, and other additive materials can improve the same mechanicals that we saw in this test. My opinion is graphene, of course, is the solution, but I'm the Graphene Council. Why would graphene be a superior material compared to other potential additive candidates?
As someone that's worked extensively with carbon black, carbon black doesn't just impact one set of properties or another. It changes the rheology, it changes the flow characteristics, it can change the cross-linking mechanisms in some systems, and it's not an inert material. We've been working with carbon black at Vibrance for at least 50 years. And there's a lot of different types of grades of graphene of carbon black out there. And yeah, you can get some benefits from it, but can you add 0.1% of carbon black and yield meaningful benefits from it? I'd like to see that if you can.
Yeah, that's a good point, because at that 0.1% loading, you could still do stuff with low viscosity resins, so you can infuse.
That's right.
Running through an impregnator for a pre-preg machine, you don't have to worry as much about it changing the viscosity drastically. It just gives you those incredible enhancements with very minimal impact to other factors.
And this might be another good point to mention something, that if a graphene producer or even an end user wants to test and see how a material compares in this test so you can do a benchmark against these other materials, we are accepting candidates for further testing that'll be into this test at the exact same protocols. We will test at 0.1% to compare with the other favorable results. And as both of the gentlemen have said, the other part of our testing is to look at other load factors, including a lower load factor than a 0.1, which has important commercial application. But to answer this particular point, with the very low load of graphene, it means you retain the majority of the host material's key characteristics, which is why you use it in the first place. And the other thing we've seen with graphene, and this applies whether it's in composites, plastics, concrete, cement, other applications, coatings, graphene, I have yet to see where graphene has a significant negative trade-off for the benefits it brings. And typically it brings multiple benefits. When it was added to a polyurethane for strength, it made the material less flammable at the same time, which was another positive attribute. So, that's another reason is, what are the trade-offs you have with these other materials? So there may be something better than graphene, but graphene holds tremendous promise to be an extremely low load factor with minimal or negligible negative trade-offs to get those performance improvements. And that's why we continue to look at this. We have over 100 questions in total in the queue, so I'm going to go through it, a couple more of these. And gentlemen, if you see any questions that you particularly would like to address as you look at those, let me know.
Here's an interesting one. Are there standards to define the several materials in a graphene family? And Terrence, I think maybe you'd want to talk about that a little bit, because I know you've done a lot of work on.
So to answer the question about the standards and the classification, the Graphene Council, through over 100 volunteers on a standards task force that we work with, last year did what's called the Graphene Classification Framework. And it's a very detailed way, 19 different characteristics of differentiating one material from the next, including a standardized syntax for the description of the material, and including a standardized technical data sheet so that the materials really can compare apples to apples, one to the other. Now that has been licensed to ISO to turn it into an official technical specification. And next week is the balloting for that. So this first of all, it's super fast to do this in that period of time. Secondly, it's by the graphene industry for the graphene industry to understand and differentiate one material from the next, because the details of the different morphologies are critical to how it performs. And this will become an ISO technical specification that anybody in the world can use. And the Graphene Council continues to work on that body of work. We retain the copyright to it, and we've licensed it to ISO. And if anybody would like to learn more about that, we're happy to share that. That's what we do. But this is really important. And further to that,
Yes.
the Graphene Council has conducted a significant amount of material characterization and testing. We run a verification program for graphene producers, which involves an on-site physical inspection of their facilities, their production methodologies, and a testing of the material. We've had 5 companies go through that process this calendar year. And that's the most thorough examination of the graphene supply chain possible. So we do that as well. And part of that is the testing and characterization of the material. So Paul, thank you for pointing that question out and asking about that. It's a really critical part because
yes, it is.
One of the reasons that the composite sector has not embraced graphene more than we thought it should up until now is that many composites companies tried what they thought was graphene years ago when there was a lot more attention to it, and they weren't successful with it. One was they didn't have the dispersion techniques and skills that a company like Vibrance has. Another reason is that many times the material was not actually graphene, and it may have been something other than that because it wasn't properly tested, vetted, and characterized. And so that's also part of what we're doing here is to make sure that we deal with appropriate material in an appropriate way to get the intended result. So thanks for that question. So since I got kicked out, did you guys see any other questions that you wanted to address?
Yeah, let me jump in there with one. Somebody was asking about how many specimens were tested in each sample set to justify the statistical significance. And we went with 5 samples for everything. The reason being 5 gives us enough statistical confidence that we're happy. 10 would have been better, but then we're talking about doubling the cost of everything and the amount of time. So 5 gives us a level of comfort and confidence in our data set. That's why we chose the 5 samples for everything, and every single one had 5 samples tested.
Here's an interesting question. Among all 3 flexural properties, which one is most important? That's a good question.
Yeah, I would say it all depends on your design. I mean,
right.
Obviously, if you're laminate design, so if you're designing a laminate out there, you do first ply, last ply failure, and it's defined by the loading. And so obviously modulus is important if you need stiffness, if you're carrying a load and you don't want any strain, any flex in the material. But strength is obviously also very critical because no matter how much it does strain, you don't want it to break. So it really depends on what you're designing around, whether it's a structurally loaded part that is critical, a flight critical structure. Obviously you're going to be dialing into whatever physical property is the first ply failure. So that, it depends on your application. Paul, you got anything else to say about that?
Yes. What would you say to someone who says, hey, we can achieve the same type of gains with calcium carbonate?
I'd like to see the data, and then I'd like to see what the trade-offs are when you add in the calcium carbonate. I mean, you could certainly improve with calcium carbonate, but it really negatively impacts a number of other factors as well.
You're right, and you'd have to go much higher load factor, and then there's other complications and issues that arise.
Yeah.
Interesting. Thank you, guys. This was a neat resin test. We didn't test yet in a fiber reinforced system. And I know there's concerns about the filtering effect, right? If you're doing infusion through a stack and then you have that, I'll make a short comment about this, and then you guys are the experts. One of the things that we are going to be looking at over the course of the next year is looking at pre-preg systems and how to incorporate the graphene in that. The other is sizing of fibers. So another way of getting graphene into the system is not necessarily through the resin only, but we could look at fiber sizing and having graphene embedded in the system that way. But there are many different particle sizes, and so that's going to have an influence on whether it's filtered or not. But again, I'm not the expert here. So, gentlemen, what's the response to potential filtering of these nanoparticles out in infusing through a stack?
Yeah, well.
Go ahead, Paul.
I was going to say, you have to worry about filtration with any particle, right? So platelet diameter, particle size diameter are going to be key. And typically the particle sizes we're dealing with the platelets and that we work with in a study were small enough that I would not consider that to be a huge concern. I would expect, but then on again, you do run into interactions between particles, and it's possible in a given matrix or system that that graphene nanoplatelets decide that they like some particle or fiber or something that's present in the system and stick to it. You can't rule that out. That's going to be system and formulation specific. So.
Yeah, and you're absolutely right. At that low of a loading, I feel fairly good about it not being filtered out, but it really depends as well on the laminate. So if let's say we took a 16 ply stack of carbon uni and we tried to infuse it, that's going to be more likely to filter out than a Kevlar laminate. But I think when we move on to the laminate testing, if and when we do that, we can look at infusing the laminates instead of having a pre-preg laminate utilized for it. So that's an option we could take a look at to see how it impacts it. I could tell you I have infused with a graphene enhanced laminate. It was not a thick laminate, and it did not get filtered out, and it was a carbon fiber laminate. So I suspect we'll be okay, but we just won't know until we do the testing.
Yep. Excellent. I'm just reading through a few questions. If you gentlemen see any that you want, some of them are related to additional testing or test characteristics like heat deformation and things that we didn't test for at this stage. I would just say as a general statement, we assume that there are graphene producers out there who may want to have their material tested to see how it benchmarks. I also assume that there are going to be important end users out there, whether it's in aerospace or wind blades or automotive sector, who are interested in particular properties to be improved. And this type of nano additive graphene might be a really interesting candidate. If you have a very specific test protocol that you want, or a part or characteristic that you want to test for, this is exactly what we're set up to do as the Graphene Council, because we're neutral. That means we can source from any of our graphene producing companies for the type of graphene that's needed. And you have expertise in the companies with Vibrance and with Composites One for us to conduct the testing with our partners at the University of Maine in the Advanced Composites Center, for example, that we can optimize for a particular application. This test was not meant to answer every question about every formulation and about every test protocol. It was simply to prove in an independent scientific manner whether or not graphene makes a significant improvement. And I think we can say confidently that we know that it does. So that's important to kind of put into perspective.
Yes.
We are getting close to the top of the hour, and I know we still have tons and tons of questions. I want to encourage everybody in the audience who has submitted a question or would like to know more about this is to reach out to the Graphene Council. If you are not a member of the Graphene Council, one of the benefits of being a member is having greater access to information and connecting with subject matter experts to solve your engineering and business objectives. And so I want to encourage you to reach out to us if you think that we can be of help and you're not yet a member of the Graphene Council. And hopefully our members can attest to the benefits of being in this network. So we deal with facts, we deal with real information about how to apply these materials in a technical sense, always with the understanding that for a commercial application to succeed, it needs to be economically viable, it needs to work with your processes, it needs to be accessible, and there needs to be a supply chain behind it to supply. And those are the kind of things that we think about and we work on when we address these things. It's not theoretical and it's not just a science experiment. It's about solving commercial problems.
Mm-hmm. Paul or Terrence, let me jump in here. There's a number of questions geared around further evaluations, like asking if there's SEM and any idea why 0.1% was better than 0.5%. I'll say this, we do plan on having future peer-reviewed periodicals done by the University of Maine. So keep an eye out for that. We obviously have some ideas and some thoughts on why, but none of it is validated at this point. So I would leave it to those periodicals as they do those publishings. I will also say this, it was interesting because Dr. Stahl took me into their lab on some of the samples we looked at that didn't do well, and we looked at them under a microscope and we dialed in really tight, and we could see the ones that didn't perform as well tended to fail where we had a conglomeration of the nanoparticles. So you could see it under the microscope where it looked like a fisheye under a microscope, and then you dialed in even tighter, you could see that there was just specks of these nanoparticles that stayed clumped together on some of the bad performing ones. So that was interesting to see that. But I can't definitively say why the 0.5% didn't do as well as the 0.1%. So I'll leave it up to the University of Maine to kind of outline their findings, dig in deeper with SEM and other analyses to see what they think happened.
There's more to the issue. We've done other studies and we've seen, in other studies we've done that if you go above a certain threshold, there's a percolation threshold. If you're working with real graphene, you have to have interstitial separation of the particles, and maybe that's what you're seeing under the microscope. If you have too many particles in too small of an area, there's something called van der Waal. And van der Waal isn't a big deal at 100 nanometers, but at a couple of my atoms across in your platelet diameter, thickness, that's a significant force. And so van der Waal plays a role, and if you don't have interstitial separation between the particles, you're not going to achieve load transfer. If you don't achieve load transfer, you're not going to achieve the gain in performance. It's that simple.
And very crudely speaking to this, what we've often found, if you're not getting good results, use less graphene, which is counterintuitive. Most people think, well, I've added something to improve a performance factor, it's not working, I'll add more of it. Time and time again across almost every application area, we've seen the improved results came from using less material up to a point. And right. And for many that are not familiar with graphene, that'll sound counterintuitive.
Yes.
But that's so the 0.5 being less good than the 0.1 makes perfect sense.
And graphene isn't graphite, which if you take graphite and you load it up to 30 or 40% based upon your polymer load, and you're going to gain a significant amount of performance, right, in terms of stiffness and things like that. But this isn't what we're talking about here. This is a different phenomenon.
As Jason said, there is going to be a peer-reviewed article that will be published in Graphene and Technology, which is the official journal published by Springer Nature for the Graphene Council and for the Maxine Association. So there's going to be a much more in-depth treatment of these test protocols for those with more technical questions to it. But from my side, I think we can confidently say that graphene should be a candidate for anybody who's looking to make significant strength improvements to their composite, and that we will work with you for optimization depending on what resin system you want to use, what type of application you want this material to go into, and what kind of performance characteristics you're trying to maximize. And we, again, as a neutral independent party to this, are dispassionate about which graphene is used, but we have access to all the graphene producers who are our valued members, and we can help to facilitate those connections through our partnerships. Paul, do you have a closing statement for our audience?
Sure. I just want to say thank you for all the people that are attending and listening to us. And I want to let you know too that the process by which you employ graphene is very important. If you just take a dry powder and you mix it into a resin, you don't necessarily achieve de-agglomeration. You don't necessarily achieve particle separation. You don't necessarily achieve interstitial separation. And one more thing I want to mention too along the same lines is graphene is a material with multiple benefits. It has electrical properties. It has thermal dissipative properties. It has thermal stability enhancing characteristics. It's a material that can do a lot more than just simply improve mechanical properties of your material.
It's a great point, Paul. And we've seen, just a point of detail on that, we've seen, for example, BAC Auto, which is Briggs Automotive Corporation in the UK, which makes a monocoque road-ready car that is all carbon fiber, all graphene infused. They use graphene not only in the resin system to improve strength and reduce the number of carbon plies, they put graphene into the mold, into the tools, because they got better heat performance, better thermal performance, and it made their molds last longer. So it's not just for the part, but also, I mean, that's something we haven't even discussed today, but for the tool. Yeah. Jason?
Makes sense.
Yeah, I just want to say, the exciting thing about this for me is that we deal with a lot of different nanoparticles and we sell a number of different ones. This gives us a product that is data that we could stand behind, done with the Graphene Council in coordination with the University of Maine. So it's unbiased, accurate, solid data. So we can work with you guys, our customers, to bring you a system we're confident in, that's market ready, that we can help you immediately coming into your shop, dispersing it into your system, and giving you enhanced results. So we're excited about that, and we're happy to work with you. So reach out to us if you have a need.
Well, on behalf of the Graphene Council, thank you, Jason and Composites One, for your support, your time, your expertise. Paul, for you and Vibrance and the team at Vibrance, because it's not just yourself. You've got a whole team of people that helped us with this. And a shout out to the University of Maine and the Advanced Composite Center for their assistance with this project. We want to thank everybody for bringing this over the line. And we hope this was informative and helpful to our audience. So thank everyone for attending. Stay safe. Thank you.